So let's try to think of a different scoring scheme. Recall from chapter 1 that we had this term document incidence matrix which indicated the presence of a given term in a given document. Presence or absence. It was a binary matrix. Now we weren't keeping track of positions of terms in documents here, and we weren't also keeping track of term frequency information. We weren't keeping track of how many times a given term appears in a given document. But we did think of either every row as a row vector, a row vector for every term, or a column vector for every document. Okay, so this matrix can be thought of in two different ways. And for the purpose of this lecture, we're going to think of this matrix as composed of a set of vectors, a set of column vectors for each document. And each column vector is denoting what terms appear in that document. Okay, for example, Hamlet contains the terms Brutus, Caesar, Mercy, and Verser. Okay. So each document can be represented by this bit vector or this binary vector whose elements are drawn from the set 0 and 1 and whose length, okay, so the length of each vector is the size of the vocabulary. So if this is the vocabulary, the size of this vocabulary V is given as the cardinality of this set V. So V is the set of terms here. Okay. Now we are going to extend this uh, binary term document incidence matrix to incorporate term frequency information. Okay, so instead of just denoting the presence or absence of terms in the matrix, let's keep track also of how many times a term is appearing in a document. So now we are going to say, for example, we're going to keep track of the fact that the term Antony appeared 157 times in the play Antony and Cleopatra. Okay, we're going to keep track of the fact that Calpurnia occurred 10 times in the play Julius Caesar. So this is called a count matrix. We are also counting how many times a term appears in a document. So either an entry is going to be a 0, indicating that the term does not occur in the document, or it's going to be equal to the term frequency of a given term in a given document. Okay, so these are term frequencies. And now each document can be thought of not as a 0-1 bit vector, but as a count vector. The length of that vector is still the cardinality of the set V. Okay, but which is basically the size of the vocabulary here. But each element of this vector is a natural number. Okay, it's a number in the set 0, 1, 2, and so on. Okay, that's what this set n is. But note that even in this count matrix, we are still not keeping track of the positions of words in the document. For example, if there is a document, John is quicker than Mary, this document will have an identical count vector as the document Mary is quicker than John, because the same set of words appear in both the documents the same number of times. It's just the ordering of these two words that's different. Okay, so they have the same vectors. Now this is called the bag of words model. In the bag of words model, what we are doing is we are treating every document as consisting of a bag of words. And we discussed this in a previous lecture. What's the difference between a set and a bag? A bag can contain repetitions of items, whereas a set cannot contain any duplicate items. A bag can contain duplicate items, and so because we are keeping track of this term frequency information, we are keeping track of how many times a given term appears in a given document. And so this document can be just visualized as a bag of these terms. Okay, in particular these 4 terms. So note that we are taking a step back with respect to the positional index. Okay, so this bag of words model is not keeping track of uh, positional information or the order of words in the document. It's just mixing them up, treating them as if they are contained in a single bag without any ordering. And we'll see how to extend the solution that we'll develop in this chapter to positional indexes later on. For now, we're just going to look at non-positional indexes using this bag of words model. So recall that the term frequency of a given term T in a given document D is the number of times T occurs in D. And now we are going to use term frequency to compute the query document match scores. Okay, recall that there were 3 problems with the Jaccard coefficient, one of which was that it does not consider the term frequency. So now we are trying to develop a scoring scheme that is going to incorporate the term frequency. Okay, so in general, we're going to say that a document which has 10 occurrences of a given term, of a given query term, is more relevant than a document that has only a single occurrence. But this quantification of relevance has to be done carefully. Okay, it's not that just because the document contains the word 10 times that it's 10 times more relevant. Okay, relevance is not something that increases proportional with term frequency. Okay, I mean it may increase with term frequency but not necessarily proportional to term frequency. Okay, and one of the things you have to keep in mind here is that in IR the word frequency indicates just a count. Okay, it's not sometimes frequency is thought of as a fraction or the number of times something happens um, in a given uh, uh, universe of possibilities. So it's usually thought of as a fraction, but here it's just a simple integer count. Okay. So here is another score. So you can think of TF of T comma D as a score. Okay, and one of the scores that you can come up with between a query and a document is the sum of the term frequencies of all the query terms in the document. Okay, so for example, if you take a query like capital of India, and if you have a document D1, okay, and this is the query, then we can say that uh, the score between this query and this document is the term frequency of capital in the document plus the term frequency of the term off in the document plus the term frequency of the word India in the document. Okay, so you're just adding the term frequencies of all the query terms in this given document. Okay, this is the score between Q and D1. You can do this for other documents in your corpus and see which document has the highest score. But as I just said here, relevance is not something that increases proportional to the term frequency. So here um, if a term appears 10 times in a given document, it's going to contribute a weight of 10. Whereas if a term appears just once, it's going to contribute a weight of 1. Now it's more realistic. Again, this is based on empirical experiments. It's more realistic to go with a score where, um, sorry, where the weight is not exactly the term frequency, but it grows as 1 plus log of the term frequency. So instead of growing like this, okay, if this is the term frequency and if this is the weight, in this particular scoring scheme that I described, the weight was the term frequency itself. So this would be a straight line, okay, at an angle of 45 degrees, okay, where the weight, the value of the weight is equal to the value of the term frequency. But what we are saying is that the relevance does not increase proportional to the term frequency. It actually increases something like this. Okay, that means when the term frequency is 0 and when it becomes 1, so if a document does have a term, if a document does have the term T in it, it's definitely much more relevant than a document which does not have the term. A document that has the term 2 times is more relevant than a document which has the term just once, but it's not doubly relevant. Okay, so I don't know if you're familiar with the idea of marginal returns, but as your values grow higher and higher, the increase in this weight becomes lower and lower.
Sir, excuse us. Sir,
Yes. Yeah.
can you repeat the last point, because the character what you're writing is, I think there is a delay in displaying the characters what you're writing.
Okay.
So from the previous, the last point, can you repeat with the content so that it will be easy for us to follow?
When you say the last point, this slide or the
From
next
the
slide?
relevance. Yeah, this slide, this slide.
This slide. Okay.
Yes.
Yeah.
From the
So
example.
okay. So what I was saying was, in this particular example that we saw, the weight that we were giving for the occurrence of a term in a given document was the term frequency. Okay. So if we plot, so think of how much weight we are assigning to a given term appearing in a given document. Okay, what we are saying is that the weight was equal to the term frequency here. So if we plot the term frequency along the x-axis and the weight along the y-axis, you get a 45 degrees line. Okay, W is equal to T. That's the equation of this line. And okay, any point along this line is basically of the form x comma x, because the weight is the term frequency in the previous scoring scheme. But now we are going to look at a more complicated scoring scheme where the relevance does not increase proportionally with the term frequency. Here it was increasing proportionately with the term frequency. The idea is this: when the term frequency is 1, that document is definitely more relevant than a document which does not contain the term, right? But a document which contains the term 2 times is not twice as relevant as the document which contains the term once. Okay, so this is the score, this is the weight when the term frequency is 0. This is the weight when the term frequency is 1. This is the weight when the term frequency is 2. This is the weight when the term frequency is 3. So what we are saying here is that the weights are going up as the term frequency goes up, but you are getting diminishing returns here. Okay, so the gap between successive values of the weights is going down. And that is what leads empirically to good results. I mean, you shouldn't assign a document which contains a term 1,000 times to be 1,000 times more relevant than a document which contains the word just 500 times. And again, the way to intuitively think of this is that if you do such a thing, then longer documents will, which have more occurrences of that term, will get an unfair boost in the score. In fact, what many spammers try to do is they create these spam web pages which have many of the important keywords just randomly appearing over the page with very high term frequencies, so that they can be ranked highly with respect to those query terms. We'll see how to detect spam pages later on. Okay, and that's one of the other things that we're going to look at, the idea of page rank, but we're not going to look at page rank here. So the weight that we are talking about here is a more sophisticated weight than just the term frequency. It's actually 1 plus log of the term frequency. Okay, so if a term appears in a given document, then this is what the weight will be. Okay, the weight that we'll be using. If it does not appear in the document, the weight will be 0 as before. But if it appears in the document, the weight won't be the term frequency itself. It will be 1 plus log of the term frequency. Okay, that is it. It's going to be this particular curve. It's not going to vary according to this straight line. Okay, so if the term frequency is 0, the weight is 0. If the term frequency is 1, the weight is 1. Why? Because log of 1 is 0 and 1 plus 0 is 1. If the term frequency is 2, then log of 2 is 0.3. Okay, this is log base 10. Actually the base doesn't matter, but that's something we'll come to later. But for now, just think of it as log base 10. That will be 0.3. 1 plus 0.3 is 1.3. If the term frequency is 10, then log base 10 of 10 is 1 and 1 plus 1 is 2. If the term frequency is 1000, then log base 10 of 1000 is 3 and 1 plus 3 is 4. Okay, so in this way you can calculate what the weight will be. And again, if you want to score a query document pair, you'll just add up these weights for all the terms appearing in the query. Okay, just as we were doing here, except that the score is not the term frequency itself here, it's going to be 1 plus log of the term frequency. Okay, and you'll just add them up over all the terms in the query. Okay, and assuming of course that if a query term does not appear in a document, then that weight will be 0 for that particular query and for that particular term and document. And if none of the query terms is present in the document, then the overall weight will be 0. Because the individual weights will be 0, so adding up zeros is just going to give you a 0. Is that any questions on this? We can take a break now, but if you have any questions so far, do ask them at this point.
So one question, sir, like now we're counting the number of times the terms are appearing in the document. So instead, if we if we can count the density of the terms, like the number of terms, number of occurrences divided by the length, like that, would that also could that also work?
Yeah, so what you're trying to do is you're trying to address two of these problems here at the same time by a scoring scheme, which is not only taking into account the term frequency but also trying to normalize for the length, right?
Yes, sir. Yes, sir. No, not.
Yeah, so yeah.
Yes, sir. Yes, sir. Yes, sir. Yes.
Yeah. So I mean, yeah, you can think of that, but actually even with that scoring scheme, you do have to keep in mind that you want to maintain this property. Okay, you want to maintain this property. So rather than just term frequency divided by the length of the document, you should take 1 plus log of the term frequency divided by the length of the document. Now again, where did this formula 1 plus log of the term frequency come from? Again, it's based on empirical experiments. You can intuitively see that this particular formula does not result in an increase that's proportional to the term frequency, but there could be other formulas. Yeah.
Sir, excuse me, sir. Sir, can you kindly continue after the break, sir, please?
Okay, sure. So just before the break, we were looking at a way to score the proximity of a query to a document. And the way we're going to define this score is by defining a weight for the occurrence of a given term in a given document, and that weight we will be adding up over all the query terms to get a weight between the query and the document. Okay, so the score for a given query and a given document is the sum of the scores for the individual terms in the query to the document. Okay, and each of those scores is what we are calling as W of t comma d. So the score between a query and a document is the sum of the scores between individual terms in the query and the document. Okay, and initially in the previous slide, this weight was nothing but the term frequency. So we are trying to define a proximity score between a query and a document, and we are saying that the overall score between a query and a document is going to be the sum of the scores between every term in the query and the document. Okay, and this could be defined very simply as just the this particular score between a given term and a given document, which is how much weight we are giving to the occurrence of a given query term in a document, could be defined as just the term frequency, or how many times that query term is appearing in the document, or more realistically, we have to come up with a score which does not increase proportional to the term frequency. That is, initially the increase is high, but then it doesn't exactly plateau off, but the increase is not so much as the term frequency increases more and more, right? So if the term is already occurring 100 times in the document, moving to another document which has the term 101 times should not make that second document to have a score too much higher than the score for the previous document which had the term 100 times. So compare that to a scenario where you have two documents, one of which does not have the term and the other of which has the term appearing once. Okay, the difference between the scores in these two cases is going to be large compared to the difference between the scores of two documents, one of which has the term 100 times and the other which has the term 101 times. And this is a function which actually behaves well. It behaves according to the desired behavior, where as the term frequency increases more and more, the increase in the value of the weight is smaller and smaller and smaller. Okay, so this gap goes on decreasing. And functions which behave like this end up being good functions in terms of, that is, if you work with such weights, you are bound to get better results in your ranking than going with just the plain term frequency count. Okay. Now, we also saw that apart from term frequency, we need to take care of two other things. We need to ensure that the weights also incorporate how rare a term is in the collection as a whole, because stop words should not be given much weight. Okay, just because the stop word in a query appeared in the document should not be given as much weight as, say, a rare term in the query appearing in a given document. Okay. The occurrence of a rare term in a document is more important than the occurrence of a frequent term. Now, let's look at a way to capture this, and the flow here is going to be that once we are able to capture this, we will capture this via a separate score. Okay, and then we are going to combine these two scores into an overall score which will satisfy both these properties. So right now we've seen two scores which incorporate term frequency. One was the term frequency itself, and the other was 1 plus log of the term frequency. Now we're going to look at a score which incorporates how rare or how frequent a term is in the collection, giving more weight to rare terms. Okay, so that's going to be some score. And then we're going to combine these two scores into a single score.